All right, thank you all for coming. We'll be talking about the IBM 5100. Most of the community here, I think, is familiar with some of the history of that. So I wanted to dig into kind of the P.A.L.M instruction set of that system. So I kind of want to go deep dive and technical, not into the hardware, but I am trying to stick to the schedule. So I might gloss over some things and talk kind of fast. There will be some website information after this. Okay, so this is why I'm dressed like this. I wanted to replicate this old IBM advertisement. We call him the smug guy. Usually when you go to Google and you Google the IBM 5100, you'll probably see this picture show up. IBM was trying to commercialize this system to businesses, and so this smug guy, he's holding it, obviously, so I got the matching tie and the custom pants from France. First part of them, I'll talk about a review of the 5100, and in the second part, I'll get to the more technical aspects of it. And then at the end, a few minutes, some new developments in the last year that the community might not be aware of. All right, so in 1983, Paul Friedel published an article in PC Magazine about the SCAMP prototype. So 1983 was the 10th year anniversary of the SCAMP. This year, 2023, is now the 50th anniversary of the SCAMP prototype. And for those not familiar, the lineage of here of the IBM PCs in 1981. But there was this portable system in 1975, and so SCAMP was the prototype leading up to that system. One kind of special thing about the SCAMP, it actually doesn't have a power supply. That's why it's kind of sleek in the back end. When they went to the commercial, it gets much bulkier on the back end because it has to fit the power supply. When they prototyped this system and demoed it, the power supply was underneath in a cabinet. And it uses a regular tape cassette, and we'll talk a little bit more about that. They didn't use that in the production systems. But there's this, the interesting thing in that article, which is, it's several pages long, but I zeroed in on this, the relationship to this IBM 1130. They didn't have time to develop P.A.L. from scratch, so they borrowed from the IBM 1130, which is what that system looks like. It came out about a year after the IBM System 360, and the computer itself, I think, is underneath this cabinet, typewriter, teletype kind of system here in the center. But I zeroed in, they talked about P.A.L.M microcode, and I was like, what does P.A.L.M mean? I wanted to learn what was that. Nowadays, we take for granted, we'll call it the x86 instruction set and that legacy. So what is this P.A.L.M instruction set about? All right, P.A.L.M, in Paul Friedel's article, he says it means put all logic in microcode. P.A.L.M does not mean the P.A.L.M Pilot. I've actually had people ask me how they had, the P.A.L.M Pilot, I think, is a Motorola 68000 or some variant of that. So P.A.L.M is not the 1990s P.A.L.M Pilot. We found a document, an IBM internal document. Christian Cordy, a gentleman at an IBM museum over in Germany, he uncovered this internal document called the Instruction for Use of the Assembler Generator. It was written by H.J. Myers. If anyone knows about him, I'd like to learn more about him. I assume that's his internal IBM phone number, but the document is dated from 1977. And it's relevant for a couple reasons. It's one of the first where I found a reference to P.A.L.M. A few pages into that document, it kind of says, how do you run this general assembler? And you give it this P.A.L.M. command line argument. And then the next paragraph, it says it takes 45 minutes running on a 5100 to completely process all of P.A.L.M. as an input file to produce the P.A.L.M assembler, which is in 6 P.A.L.M. So what's 6 P.A.L.M? There's some handwritten notes in this document, and 6 is just the 6 file that's on the tape. This parenthesis lib is in APL, how you list the files on a tape. So somebody, it may be Myers himself, the index, this is the full extent of the general assembler, and the byte size associated with that. If anyone has that tape, we would love to find that tape. I don't have it. This is what the P.A.L.M processor looks like. And I guess to back up a little bit, my understanding is P.A.L.M is referencing more of the instruction set. I don't know if it means the hardware arrangement itself and how P.A.L.M is implemented in hardware. These two chips on the processor, these are not processors themselves. These two chips are each one 64 bytes of the register file. So the first 128 bytes of the system are right here. They're address mapped to these two chips. And 15 megahertz clock over here. There's a little jumper on this side. The 5110s will have this. This jumper will make this processor compatible with the 5100 or the 5110. You just move it from one side to the other. So that's the gist of what the processor looks like. There's not a lot of TTL chips. It's implemented in microcode. So the add instruction is on one of these chips. And I haven't narrowed down exactly which one, but it's a card about this size. All right, so in that general assembler, it kind of gives an example of how to run it. And you answer a few questions when you first start it, and then that 45 minutes, it's generating A.P.L. code. So the IBM 5100 is kind of famous for that A.P.L. relationship. I'm not an expert on A.P.L. itself, but basically it makes these A.P.L. functions, and that's an interesting usage of A.P.L. And that usage is also earlier in the IBM System 360, where it was helping to define the instruction set of the system. And so these are not the instructions themselves, they're just A.P.L. functions, but this is just 4 examples, but the full set is about 12 A.P.L. functions. And you pass different parameters. These are the actual opcodes. These ones in red are the actual assembler mnemonics for P.A.L.M. So if you want to do an AND, you use the ALU function starting with 5, and then you pass your user-defined operands after that. If you want to add a byte, you use ALU with 8. To put a byte, this IO request, the branch, if 2 values are equal, it's a branch control with 2 and 10 are the opcodes that are passed to it. So all of that helps define the assembler that runs natively on the 5100, and that's an interesting use of A.P.L. All right, so during COVID, we all had lockdown, and I guess my hobby during that lockdown was studying more about the IBM 5110. I met a retired IBM engineer, and I was able to get the fully working 5110 from him, and I just learned, started learning more about the system. I actually didn't know that these systems even existed before around 2019. So at the end of Paul Friedel's article in PC Magazine, he has a list of a whole bunch of people that were involved in the SCAMP production. So during COVID, I said, well, let's see if I can find these people. They're probably bored as well. So I started emailing out, and I found a couple of them. Dennis Robertson is still active in the industry. He was the lead engineer for the IBM 5100. He was also involved when he was younger in the SCAMP development just a few years earlier. So he worked directly with Paul Friedel. And Hal Pruitt, another contact, he's not listed in that article, but Hal Pruitt, he was the founder of Core, and he ended up building several accessories for the IBM 5100. And so I emailed them, I asked them a few questions, and so these are some of the highlights of some of those questions. I asked Dennis, what do you recall about the P.A.L.M. processor? And he states it was developed in Boca Raton. Now I grew up in North Florida, so I'm pretty familiar. For those not familiar, Boca Raton's north of Miami, south of Melbourne, and in the vicinity of NASA, Port Canaveral. And Boca Raton was eventually what built the IBM PC at that location, but they're also involved in the Series 7, Series 1 systems. He mentioned some of the direct people involved in the P.A.L.M. processor development specifically. He does confirm that the P.A.L.M. processor is also, as far as I know, there was only one SCAMP prototype, and it is, I confirmed a couple months ago, it is still on display at the Smithsonian on the first floor. I'm hoping later this year I'll be able to talk to them and get to explore some more documentation that they have available. They have several manuals that would be interesting to learn more about that prototype. Dennis also emphasized, he says, it was the P.A.L.M. processor itself was intended for industrial applications, and that can mean a lot of things. But industrial applications, you're in the vicinity of NASA, so maybe test equipment. You know, not typical desktop PCs as we would think of them, but industrial things that help industry do their things, you know, factory management, automation kind of things. That's what it was intended for. But it ended up, they said, hey, what should I use for building a first portable computer? And P.A.L.M. ended up being what was recommended to IBM internally. Remember, Intel was just getting started around 72, right? So they weren't as well known. Early microprocessors were still slow. It took them a few years to kind of advance to be fast enough to compete. All right, and I read some articles that suggested that the P.A.L.M. was somehow related to Apollo. And Dennis basically says no. He says maybe it's possible, maybe it was a backup. You know, IBM was in case NASA needed some alternative, or, but basically he says no. He doesn't. It's not like P.A.L.M flew on any spacecraft, as far as he knew. And he's reminding that it was intended for industrial computers, so it may have ended up in some NASA test equipment, but not directly involved in the Apollo program, as far as he knows. But he does elaborate that it was used by the Department of Defense. I've met some old timers at Lockheed, and I can speak to that or confirm that some of the old timers have talked about, yes, they've acquired 5100s and their work in the 70s. Used in banking also. You know, you've got this portable computer that you can now just plug into a wall, you know, at home. It truly was a portable system. So that power and weight size. He says other government agencies. So to me, that means two things. I think of IRS as the other government agencies, and I say that because I found not sample, but fully available applications from IBM for doing W-2 entries, for example. So data processing on W-2s was not very exciting, but that's big business, right? That's a government agency. You can imagine other agencies also, you know, the other three-letter agencies using them over in Europe to relay information back home. Okay, so then I asked him about what's up with this tape recorder that was on the scamp. And I thought it was just a prop, like maybe it wasn't really functional. And he says, no, it actually was very functional. However, it was very unreliable. It was so unreliable that they would load up things before they're doing presentations the night before and just leave the system running to be up and running for the demo the next day. I have the carry recorder, or one of them, on display out in the exhibit hall. One of the interesting things is you don't see like a fast forward play button on the front. You have to kind of move this up and then slide it left and right to fast forward and rewind. There's no tape index, so yeah, it's a very bare bones tape recorder. First available, it was Philips over in Europe, and then when it made it over here a year later, the brand was Norelco. All right. Then he elaborates, like, okay, in the production system, IBM, you know, was notorious for using their own in-house stuff, but in this, right in the mid-70s, they're making an exception that they went to 3M to say, hey, I need a more robust portable system. And the 5100 isn't the only one to use these tapes. Some of the Tektronix systems also use it. About 300 byte capacity. It's a 300-foot long tape. Some people seem to get upset when I call it a QIC tape. There's a technicality there. It's not really, QIC means different things. QIC is quarter-inch tape. If you want to find one of these tapes today, you'll go to Google and you'll Google QIC. So that's why I refer to them as a QIC tape. But that's not quite technically correct to some people. So, but
you can talk about why later.
Yes, yes. Then he said the Rochester, Minnesota, they did want to have the 8-inch floppies available for this system, but they were already a little bit behind. When the SCAMP first came out, the A in SCAMP means APL, and it was really intended to be an APL system. But they prototyped the system, they tested and talked about it, and they said, no, we really need to put BASIC on this system. And so I think that cost them about a year. I think they could have fielded the system a year earlier, but they had to figure out how to implement BASIC on this system. We'll talk a little bit more about that in a moment. And they think they just ran out of time to add the disk support to that system, and it would just kind of violate that idea of portability. 8-inch floppies were never portable. And this 3M DC300, DC was data cartridge, and that format worked quite well for them. All right, so Hal Prewitt, I'm not sure if I'm pronouncing that right. He grew up in Florida, and he's famous for founding Core International. He's still available, happily retired. Fisherman, flies airplanes, drives race cars, you know, lives a good life. I think he ran for office also there in a county in Florida, won. So still active. So I'll talk in a minute about what Core is. Well, two things. Core is like a little network system that was available that he developed, and I'll get into the specifics in a moment. But he also developed this PC51, which was, you could emulate the entire BASIC capability on an IBM PC. And basically I asked him, is any of that still available? And he says there are copies of PC51, but none of the CoreNet LAN hardware is available. So if anyone has that, we would definitely like to find it, and I'll show some pictures in a moment. But also this footnote, in early 90s, Core had grown. It was a much larger company. They had larger data storage equipment. AWA was a subsidiary of Sony in the early 90s, and I think fully acquired a few years later. I asked Hal, could I get a copy of PC51? Could we put it on WinWorld for archive purposes? He hasn't responded. He had a rough winter in Florida last year, is my understanding, is the last update I had from him. So I'm looking for that software if anyone knows of the PC51. His hands may be tied because he's basically sold everything off to Sony, so I don't know if that's the holdup there, but he is saying there are copies of it available. Runs on DOS, MS-DOS 2.0, so it's a lot of us could run it. So CoreNet was his storage networking. You could attach up to 8 hard drives to your IBM PC and have them share these devices across each other. And what's exciting to me is he confirms that it was all in P.A.L.M assembler. He didn't need any special cards. He did not use the asynchronous COM or parallel card, which, I mean, we can replicate that system today. I'll talk more about P.A.L.M in a moment, but we know enough now that we can talk to, on the back side, there's these 3 plugs on the back that are the external interfaces. And so we could replicate the CoreNet. He mentions a driver in the advertisements. That driver took 1.5K of memory. That could be an issue for some people back in the day. The hard drive interface that he built, I think it was a 10 meg and a 25 meg option, and then you can get multiple of them. He refers to it as SASE. I haven't heard that, but he says it's a predecessor to SCSI. I mentioned the driver that took a K and a half of memory. And it was transparent to users of the system. Like, usually you'll do D80 to refer to the first disk drive. If you want to refer to this hard drive, you just substitute D08 for that device. But you didn't have to learn anything else beyond that. So it was very plug and play to add this hard drive to this legacy system. So in addition to that, Hal sent me some PDFs and presentations of newsletters from his core, and I hadn't seen that anywhere else. I want to send that on the VCF and get it more properly archived. In this one, he talks about the advanced basic. That's kind of an oxymoron, right? Actually, the 5110 does have some advanced features that you don't see in the microcomputers, and I'll talk to a few of those features in a moment. But he throws out this number of 30,000. He's like, there's no more 5110s and 5120s being built, but he's got this customer base of up to 30,000 to sell these systems to, that they've invested a lot. These are not cheap computers, and they've built their software and businesses around using this. But that's the number. I asked Dennis about this number also. So that's the number we're thinking of, how many in existence of this system. It's in that ballpark. It's not like there was a mass production of hundreds of thousands or millions of these. They are a rare system. I put them on par with the Sol 20 in terms of rarity and how hard to find them. Okay. He sent me this about PC51. It's an early advertisement, basically shareware. It's like 1984. You send him $50. He sends you 2 disks. You can try PC51 on your desktop PC, and you can try it on the IBM PC, compare the performance. If you like it, you send him $3,000 for the final product. It's quite a bit of money, but he's found his niche, right? He's going after that customer base. The number I heard, he sold about 3,000 of them, so that's quite a bit of money involved. I think it's a little funny, if you send the disc back, he gives you a $25 credit after you spent your $3,000. I think that's kind of funny. He also sent me the manual of the PC51. I won't go through that. I'll have that available on the website, and I like to get it on VCF archived properly. So interesting things about the BASIC, and this is interesting features on the 5110. The 5100 had some similar, I don't want to say unique, but unique or different from the microprocessors. But it had this form command that so let me back up. You could open a file, it had up to 10 file handles that you could reserve, but you could pipe that file to the screen, and you use this little code. 002 means the screen. You're building up your form. This is a sample little data entry form, name, address, city. And you say, I want to put that on a screen, and then you change this if you want to go to a file properly. You use the form keyword, and you have to use this position index to literally say, hey, what offset starting from 0 at the top left do you want this labels to appear? What variables you want to put it in, how long. So you don't have to write the code for like handling the user input, right? This handles all that. I want a form input here. So that's convenient. I haven't seen that in any of the microprocessor or later microprocessor basics. You can also specify the format. So for business computing, they're very particular about their financial reports. Some have strict requirements on that. So you can specify that using this pick keyword on how you want your results formatted, whether you want $signs or not, you want commas or not. Also for international business, they had other character sets, so you can have the proper symbol for the country that you're in. So that's an interesting feature. Then it also has, you have file indexes, but you also have this FLS, S for system. You have the system file. And it's 35 bytes long, and it kind of changes the behavior of system depending on what byte you write into. And to me, that's interesting because it's like a super early version of like the Windows registry file. You write something, and the OS now reacts to it. You can turn the display on and off. You can make the audio alarm, the precision of your floating points, things like that. And you can change the aspect of the system without adding new keywords, the basic. You just define this kind of format of the file. So that's an interesting feature. Function end, you can have a multi-line define a function. So in the more recent, for example, I have a PC Sharp 5000 out there on display, and you only have one line. You can do functions, but the more modern microprocessors use this, it can only fit on one line. So it's hard to document and describe what that function is doing. This one you can do a multi-line, so this is a factorial example. Simple example there. To do user-defined functions, 10-line, whatever function that you want to define with arguments. Laundry list of some other unique features, and I want to home in on this one. You could define, so they don't call it macros in the manual, they called it function keys, and you could define key 6, which means you hit the command on the keyboard and 6, and you can have pretty elaborate macros defined. So if you want to train your operators, I need to do this operation, hit command 4 or command 6. Pretty elaborate macro capability, and that's probably the legacy. You know, the IBM 5100 didn't have the row of F keys like the IBM PC did, but it sort of predates that idea. Function keys were added to those keyboards in the early 80s, so that's an interesting feature. And you can save and load your macros to a file. The merge command, you can merge in other basic programs. And this run command was interesting. Run has parameters. You put comma and you say P equals D. That means anything going to the printer, you now redirect it to go to the display. So if you want to test your program without wasting a lot of paper, you just redirect all your printer output to go directly to the display. So that's a neat little feature that it has. It has some built-in constants for like pi and some unit conversions. So that's interesting basic features. Now it lacks some features also. There's no peek and poke and there's no syscall. I'll talk in a moment about that. But basically the system responds, you type your input and you have to press enter. And this kind of destroys the ability of making interactive games. You know, WASD, you want to respond to those key presses, right? You can't do that from the BASIC. You can do it from the P.A.L.M assembly, but BASIC itself, you could make a battleship type game, enter your coordinate and press enter, but for an interactive game, just pressing a key and responding to that, I haven't found a way to do it in the BASIC. Quick little note, on the basic keyboards, there's 2 blank keys. That's not a mistake of the keyboard. It's in the manual like that. There are 2 blank keys or not marked keys. I don't know why they're blank in the manual or on the physical keyboards themselves. You do press them and you do get these keys. You'll get, it's not an X, it's a different version of a multiply when you press this top one. Different than what's on the keypad and different than X. It's a different symbol altogether. It's a more centered X. It might be an APL X. Which, by the way, on the basic models, all the APL symbols are still available. So you could pretend to do APL on the basic systems. If you hit this blank one here, you get a little backwards arrow. So I don't know the story of why they're blank, but it's not an incorrect keyboard to have those blank. Also, this the lineage of how we have enter now, right? They're calling it execute, return. I think there's an interesting story there. I've seen in the systems out in the hall, I kind of pay attention to the lineage of the systems and how the term of the enter key evolved over time. There is no clear screen. So when I first got the 5110, Dale Luck was the IBM engineer that provided that to me. And I thought he was kidding. I was like, what system doesn't have a clear screen, right? It must be some command that I don't know about. And I read through the manual, and there is no, you can't command the CRT to actually clear. You clear the screen by writing 16 empty lines. And even in the executive ROS itself, it clears the screen by writing to a bunch of spaces to the top of the screen to fill up the screen. And you think about why that is. The system, and we'll get more into it in a moment, is emulating some legacy IBM mainframe systems. And they use line printers, right? When you have a printer, there's no screen. So they never built that idea of clearing the screen. So that's interesting to me. So speaking of peek and poke, I was doing some research for something else, and I found this in the letters to the editors. And that's one of the things I miss about old magazines. Nowadays in social media, we're overwhelmed. An article will either get 2 comments or 20,000 comments, and no one's going to sort through 20,000 comments. We don't like censorship, but I think there is something to be said for a little bit of prudent filtering. And so letters to the editors, they chose, good and bad for the most part. So in this letter, this Ray from the Bit Barn down in Houston, he's saying, hey, you guys are claiming that the Altair invented, or Microsoft invented peek and poke, and that's not the case. He's saying Microsoft did not invent the software of the world. He calls out DEC and this RT11 system. I don't know much about that system specifically. I looked it up briefly. I think it was around 1973, but he's just saying, hey, peek and poke existed before Microsoft came around. So interesting little verification of that just in the letters to the editors. All right, time. Hopefully we're a little halfway through this. This is my halfway point reminder. So we're not going to go that deep into the hardware aspects. We'll go kind of medium deep into the software aspects. Growing up in Florida, I did cave diving with my father. So that's not us. This is some other cave. Okay, so microprogramming, what is that? What is this microcode? So you look through the IBM documentation, the word P.A.L.M doesn't show up, the word mainframe, System 360, none of that shows up. I don't know if they intentionally hide it, but they say they emulate P.A.L.M BASIC, and so we dig into that. And so that's what the rest of this we'll talk about. This is the arrangement of kind of the motherboard of, it's called the A1 board, the differences between the 5100 and the 5110. The P.A.L.M processor is kind of the only card that's really you can be shared between the two systems, and I've confirmed that. That jumper that I mentioned earlier, you just switch that and can work on the 5100. This X2, X4 is just a cross connect. That still existed, it's just not shown in the diagram on the 5100, so the processors are the same. But everything else is different. The memory, the wiring is different. I found a forum article that someone did stick a display card into the 5110. It didn't fry the system, but none of the characters showed up right because they are different character sets. So I wouldn't advise doing that. You can see APL, it took 3 slots previously. They increased the capacity of APL in the 5110. They squeezed it all into a half card, 128K there, so that's interesting. This ROS control got merged with BASIC. They got rid of the ROS control. It's now a common in language. These things in red, we've extracted the ROS, and this is their approximate size. It doesn't mean they used all of that available space. There are a lot of blanks in there. So that's the arrangement of the system. Okay, comparison of instruction sets. And so I won't go terribly deep in here. The main highlight or takeaway from this is these mainframe systems, they have elaborate instruction sets, and they're variable length instruction sets. Some instructions take 6, 5, down to 1 byte. The IBM 5100, the P.A.L.M instruction set, is more consistent. It's a half word, they call it, so it's 16 bits. The opcode is the first 4 bits. So you kind of have, in this already, you have kind of the CISC versus RISC reduced instruction set kind of internal to IBM arrangement. And that's kind of interesting. They're using a RISC system to emulate these old complex systems. And it is slower. It does take a lot more work to do all that. The instruction set is in the Appendix C. It's lacking in some things in the documentation, Appendix C of the IBM 5100. A lot of people have the 5110 before bit savers came along and digitized a lot of the old manuals and made them searchable. That was key, is really, it's been a lifetime kind of reading those documents, but key is being able to search them and find these little nuggets of information. At the very end, Appendix C, that instruction set was available. But it wasn't very well documented, and we'll get that in a moment. So how did we get this ROS information? So from the system, SCAMP, used the IBM 1130, so this evolution of it. IBM's intent was you could be able to plug in more languages to this system, so that's how it was architectured. You could plug in a Fortran. They never actually did that, but I think they had to do that even if they weren't going to exercise that option, kind of for legal reasons. 1975 is when the trial portion of their antitrust lawsuit started for IBM. So all their lawyers were on edge of how integrated their systems became. And that was pertinent to the development of the IBM 5100. But they made it where someone else could plug in another language. So that's part of the reason why they architected it in this way. These cards are devices to the main system, and so it's pretty easy to get a device and extract that into main memory and get a dump of what's in that content. But another thing to notice on the IBM 5100, the documentation, they call it controller. Remember, it was intended like for an industrial machine. They changed the terminology on the 5110, started calling it an actual processor. Up here in the diagram, it's controller, and it's now changed to a processor. So subtle, even though it's the same exact hardware. So how did we extract this executable ROS? Also a footnote, Joey Tootle was directly involved, and he did discuss this or reveal this 20 years ago in 2003. So the A.P.A.L. side was heavily discussed. I'm going to dig it more into the basic, which will get in kind of the new stuff in the past year that we're introducing about these systems. Another terminology is these are non-executable down here. They're emulated, these devices down here. So all the credit goes to these individuals. Christian Corti in around 2005 and Tom Stapleton in 2019 extracted it for the IBM 5100. And Tom Stapleton has a Git hub page that describes in details how he did it. But the main takeaway is a fascinating kind of feature. When you if you open up the box of the system, it has a switch and you can put it in the step mode. And for the very first cycle of the system, it's showing the contents of its internal executable ROS. I don't know of any other system that does that, and I hope someone calls me out on that. I'd like to see a system that does that. But it's kind of showing the guts of the software for that one cycle, that very first startup. So you have to open up the system, put it in the step mode, turn it on, and for that one moment, you get a 512-byte window into the ROS of the system. But what Christian Corti found out is you can manipulate that startup address. You do these pull-up resistors onto the address lines, and you can kind of steer what 512 bytes you want to look at. Pretty fascinating. So that's how we were able to build emulators and kind of continue interest in the system. When you first turn it on the 5110, the first 2 bytes are not instructions, they're actually data. The first byte is telling you what address do you want to really start the system at. So this is the first, it jumps, and that's the first instruction of the system when you turn it on. This Control F resets all the devices, and then it proceeds with its boot up from there. So when you go in, a lot of people are fascinated about the register mode of this system. When you go in the register mode, you don't read them left to right, they're up and down. The first byte is this 00 and then 0A when you're in register mode. So I spoke about, you put in the address, pull up resistors, you get the 512 bytes. Oh, and then they OCR'd it from there. So then you have to get the data off, right? Both of them, they did that approach. Christian Corti in 2005, cameras weren't what they were in 2019, but Tom Stapleton, he did some AI work in kind of learning these the font, and making sure that it was extracting that data. Now, all that said, I talked to Christian Corti, he said he wouldn't do it that way anymore. Now that we have these small MCUs, he would just put it directly in line with the data and kind of read it more digitally. So there's a more efficient way to do it. But how they did it with OCRs is pretty cool. Go. All right. So when you start up any of these systems, it's going to throw these numbers that say ROS and have these segment numbers. And it is checking the CRC to make sure that the integrity of the system is correct. It's doing that for the language ROS. It doesn't do it for the executable ROS itself, which is kind of weird. You're going through all these fail-safes, but you're checking kind of the external parts of the system. And those numbers are in the code itself. They go linearly at each 6K offset. You'll see these numbers. And so we can tie, if you have an error in any number, you can know precisely where it is. And then this is the actual expected CRC value after it for the 5100 system. Then in the manual, it also says what slot those cards are expected at and the sequence numbers. I call them segments for 6K segments. If you notice in the startup, it skips the letter I and O. You'll see that throughout the system because I and O through engineers, you might get them confused depending on the font with a 1 and 0. Someone says look for I, they might think it's a 1 and 0, so that's why they're omitted. So that's an interesting thing in the 70s. Okay, so this mysterious chapter 2 was kind of a breakthrough on how we were able to reverse engineer this system. And when I say we, I mean Christian Corti. He found it in the IBM Museum archive. And I say mysterious because there's no cover page, there's no date, there's no title. Nobody knows where this chapter 2 came from. Other than, You know, he just found the actual hard copy of it. And in there, it refers to P.A.L.M as the instruction set. And as I mentioned earlier, the instruction set is described in Appendix C, but it's a little vague. It says this high to low instruction, you pass 2 registers, and it's opcode 0. But this chapter 2 calls out these opcode modifiers. So if you want to do high to low, you actually have to pass a C as the last byte. And that's important if you want to understand the instruction set. So it's a much more verbose, an elaborate explanation of the instruction set. So he found that. He wrote the emulator. Then around 2015, Norbert has wrapped that emulator in a nice web interface. Pretty authentic on how you type the keys and interact with the system. So that's thankful that we found the chapter 2. One thing I did recently is I said if these have a heritage with mainframe systems, then those ROS better contain some EBDIC code somewhere in there. And so I scanned that and I looked for these, converted all the symbols in there into ASCII, and I looked for groups of 3 characters or more. And I'm just looking for words that are in the code. I didn't find much in the 5100. There were some strings in there, but not much. But I found kind of a mother lode in the 5110. There's none in the P.A.L.M, and that's kind of as expected. It's P.A.L.M, it's older or different. So I didn't find any in these portions of the ROSs. But like I said, I found hundreds of them. And here's a highlight of a few of them. So the word IBM 5100 is in the 5110 for some reason. The word microprocessor is in there for some reason. On BASIC, you find kind of the typical, all the basic keywords are there, no real surprises there. Then on the APL, it has this copyright 1976, and that's interesting that that's in there. Software, as far as I know, you couldn't really copyright it. The big vendors, the software came with the hardware. That's why they're part of the reason why they're so expensive. So I don't know exactly what they're copyrighting. I don't know if the system as a whole, the APL, where it came from, but it's there. My understanding is VisiCalc, he wasn't able to patent that because software just wasn't really patented at that time. It wasn't until like 1980, 1981, laws changed on that. So the word's there. All right, this is my intermission. We're going to go a little deeper after this, but just highlights of the character set between the 5100 and the 5110. They are different. The 5110, the second half is basically just the underscore version of the first half, which is similar to Commodore. Like the second half is really like the inverse of the first half. On the 5110, it has this, I call it like a running man set of symbols. We'll talk more about that in a moment. They're kind of funny symbols that I haven't seen anywhere else. But it's more EBDIC-like. You've got spacing between the alphabet. It's not just a linear. The other thing on the 51, it doesn't have lowercase letters. They added that in the 5110. Okay, so typical, this is one of the example assembler, how you did it on a System 360, as shown here. You type it in the keyboard interface here. Regular, kind of as we would see it today, you have your assembler mnemonics, and it gets converted into object code or machine code. The highlights here are just showing the consistency. The LR opcode, whatever that does, it's 18 or 18 in hex. 1B is this SR command. So that's kind of just people familiar with assembly language. This isn't new to them. But we want to verify this, that in the APL NX, it has System 360 instructions. So we picked one, we found kind of an island of zeros and say, okay, we'll assume code starts after that. And it matches up with IBM 360 instruction. The store command is opcode 50, branch and link. So that's confirmed, yes, it has lineage. And both the 5110 and the 5100, it had the same sequence of System 360 instruction sets. This changed, this 4720 changed to an OF20 on the 5110, but everything else stayed the same. So that's just a small window, and we're just verifying, yes, the system is using P.A.L.M to emulate this instruction set. Then I found the opcode vector table, and this helps us say not only is it System 360, but they omitted certain opcodes, and that table is, once you find it, it's clear as day. It's at the very end of the APL ROS. What opcodes they don't emulate and which ones that they did. And what stood out to me, I was reading through the manuals and I came across 0D and I was like, this isn't in the manual, what is this mysterious opcode? So I got all excited like I discovered something special, but I found the model 67 to find that opcode. It's some special variant of a branch command. But that does mean that more specifically, we've now resolved not only was it 360, but there's some evidence here that was specifically the Model 67. So if you go back in time, find a Model 67 is what the system's derived from. It's the same story on the IBM 5100. The addresses are different on where it jumps, and it's at a slightly different location in the ROS. But it's the same story. It's less opcodes. And I have this on the web page for the full. So one, I can't show it on this screen, but opcode FF is defined as something. It's used on this system. And so that is a little mysterious. I don't know what opcode FF is doing, and it's not documented in the System 360 manuals. So we verified all that on the APL side, but what about the basic side of things? So speaking of the basic, Tootle back in 2003 said the System 3 was involved, and that's kind of the hearsay. And so I kind of, what is the System 3? And a little background on that. You have a young lady here sitting at a machine. I think the hard drive of the system's in this cabinet. The computer itself is here. One thing about all the System 3s, it has this 2-letter LED on the front, and you can access that directly from the instruction set. It's this F0 opcode, and you designate which segments on that LED. So right in your machine code, you can kind of communicate to the user, like it's usually error codes. This error has happened, but that's on the front panel of all the models of the System 3. So that's interesting. And also the Model 6 specifically in 1970 had a 64 by 15 CRT. The IBM 5100 is 64 by 16, and I think that's funny because the IBM PC was 80 by 25. They kind of one-upped Apple by adding that extra line. The Apple's 80 by 24. IBM did it to themselves 5 years earlier. They added one line when the IBM 5100. They went from 6415 to 6416. I don't know the backstory on that.
Sometimes it's handy to have a status line while being able to...
Well, usually you have the applications, and yeah, when you boot up, when you load up BASIC, there is a little status line on what column you're on and how much memory is left. So,
they probably thought, let's take the existing 6414 application and make room for a status line.
For a status line on that. So that all jives. Okay, so I was reading about the System 3 Model 6, and I came across this product brochure that thought, and I saw this, and I said, hey, they're using a carry quarter in 1970. So that predates the SCAMP even, that this idea of using the carry quarter, and in here it calls it the alternate program load device, a tape cassette. It's troubleshooting for the disk system. If your disk system's having trouble, this was your backup. CEO was customer engineers for IBM. This didn't. I don't know if this equipment came with the System 3, but I think it was test equipment that the CEs brought in to troubleshoot the System 3. Another note in the Smithsonian, they had some pictures, and they do have a box full of tapes that were used on the SCAMP, that were used in the system. Our tape people, it'd be nice if they could get their hands on that. We'll talk to them and see what we can do. But maybe this is the earliest evidence of an audio tape cassette being used for digital, software code. I don't know if that's really true, but it certainly predates earlier than the SCAMP system. This is the source of that picture and information. Okay, so Glenn Henry also worked for IBM, and he was involved in developing BASIC for the System 3. And he has a great website, and I took out some key quotes that the System 3 was designed for interactive usage. We saw that picture earlier, someone sitting down and using that system. It had BASIC, RPG, it had a CRT, it was interactive. In his opinion, it was probably the worst architecture, the instruction set for making a scientific and engineering computer. He says it could do everything the Apple could do 9 years earlier, and that's including the vector graphics, actually. There was another card you had to do to make it do that. But it also had a hard drive, full 64K of memory. But you read later on in his article, and it says, but it weighed 1,300 pounds, it used 220 volts, and you had to rent it for $1,000 a month. So that's 9 years before the Apple capability-wise, but obviously much larger, much more expensive. Then he says, despite his complaints, the BASIC was actually very capable. And as you see on the 5110, it was used for a lot of business applications. That form, that notion of the form keyword, a lot of people embrace that BASIC system. And I've looked at the instruction set, and yeah, it's pretty rough. I'll put it that way. And this is a sample of it. So, I mean, it's typical kind of, you have your branches, but here, this part starts to get a little rough when you have to do kind of these expressions. That's not kind of typical, easy to read assembler language on what it's doing, but it's the same idea. You have equates for your constants, and it all gets assembled into object code. These are the manuals I referenced, kind of looking up these examples. So I've put another front end to the emulator also, and I won't dive too deep into this, but this is my work that I'm kind of proud of. And what I did was I put an inline disassembler. As you're running the code, it disassembles what you're running, so it's nice to read what's going on. But I added this little letter at the end, and B tells me that I'm in the basic ROS code. It'll change to an E if I'm in the executive ROS or A or APL. And so I set an internal breakpoint. I said I want the first occurrence of when I hit a B. And basically, this was hit a lot because it's the instruction fetch. This subroutine here, it's getting the next byte out of device 1, which is the basic ROS. And so that's the very first byte that it's getting out of the system, the C8, 20, and that's so it's emulating that instruction set. It says, okay, here's the instruction set, and it goes to this vector jump table. It has to add it twice. It does 2 times that to get the address, so it's a pointer to a pointer. Get the address, you scan in the address table of 990. The line here is off, so apologize for that. But it ends up pointing to 0BFE as how it starts emulating that instruction. First thing it does is it gets the next byte. It has to get the next operand for that instruction. Then it simulates that instruction, gets the next byte for the next operand. So that's all verified. We have the instruction fetch, and that helped me find where the basics build this chart, the vector table of all the instructions. So when I first found this, I thought, well, that's super exciting. However, I expected all this to kind of be blank. In the System 3 instruction set, like, these aren't defined opcodes. So what's going on here? Is it not the System 3? I think the next slide will answer that. But the address is so in the APL, they put it at the very end of the ROS. On the basic side, they put it at the very beginning. These are just offset tables. When you have this opcode, this is where it goes in memory to emulate that instruction. I believe all these ones that are the same are not supported opcode jumps. The one I was just talking about, the 08FE, I'm just highlighting that one. I was zeroing in on that. So what I found is I found another manual over in here, this component reference manual. And basically, there are opcodes that are valid, but they call them card codes. Not everything maps to a mnemonic in the assembler for that system. So a lot of the opcodes do. You have these move. ZAZ is like a major memory copy command. But it has these card code. I have to assume that's the legacy of card readers. Something led me, there was different tiers of card readers, so I don't know if it's a performance thing, that it could sort of compile this program using multiple cards, if that's what's going on. But I found in the component reference manual, so here's a picture right out of the manual, some of them have assembler mnemonics, but a lot of them just don't. So they're special variants of other existing commands. So that's as far as I've gotten. Between the 5110, I found some matching code. This 33 instruction, whatever it's doing, that was all the same. So there is some consistency between the two systems. They don't work dramatically different. Zeroing in on here, this MVI is setting that address, 10CE, to the FF. And this next command is copying it a whole bunch of times. So I think the next slide is showing the result of that. And in the emulator, I was able to go to that address in memory and look at it, and it's like, yeah, every time it executes BASIC, it starts off by filling in all these FFs. And I think that's a marker for people can kind of easily find where the activity is going on. And right after that, it's where it's tokenizing the BASIC, right at this address. So here's a 3-line BASIC command, assign the B, which it equates to 72. 40 is hex for decimal 64. I doubled that number, and you get 80 instead of 40. It's a bidirectional pointers. These are addresses, so the end of this command points to the next one. The last command, this is only 3-line program, 30, it's 0 because it's the last command, there's nothing to point to, but it's bidirectional, you can point back to the previous one. As you add lines, like this will get crazy, it'll get out of order, not everything's linear, because it manages linked list. In BASIC, it talks about garbage collection, even back then, well before Java, and part of that garbage collection is it kind of optimizing lines that you aren't using. So it's fun to watch as you add lines like between 10 and 20, how this kind of updates and manipulates. The random is just, it's 1 byte, 14 is how it stores it in memory. And so when you run your BASIC, it interprets that. 14 means run the random operation. These multiplies are 5C and so on. So that's been fun to explore and verify that the BASIC gets tokenized at that address in the system. So all through that, kind of this is the meat of it, the P.A.L.M. We've written a disassembler for P.A.L.M. and I have it documented on the web page. We're not going to go much deeper than this, but just an example of how P.A.L.M. you can have a call that translates into a 2 instruction. You increment the program counter, do a jump to the address that you're going to jump to. The disassembler made one mistake here after the D. This is actually an address. So all these Ds, they have another address after them. So that's an exception. Everything is a half word, but there are these branch commands. It has this data immediately after the instruction of where to branch to or to where to jump to. Has these move commands, decrement, kind of the typical branch commands. Halt is a 0, 0, 0. And that's what the P.A.L.M assembly looks like. And I've written up on the web page a number of examples. So this clear screen, as I was saying, like you have to go to the address and write space, space, clear across the screen. And that's, you don't send a command to the video card to just clear in one command. That takes a noticeable amount of time. So P.A.L.M, how do you use P.A.L.M? How do you put it in? Every 5100 or 5110 or 5120 has a built-in DCP Control Program. I haven't found in the manual, so I kind of discovered this by accident. As soon as you turn it on, right when it starts doing the ROS checks, you can hit Command Attention and that will put you right into the DCP. If you do it by the book in the manual, it has a few more instructions. Wait for basic, you hit hold and hit a few more keys, but you don't have to do it that way. You just do the ROS checks, hit Command Attention. But I also found if you hit a key before that, the system does this to you. It shows the key code of the key that you pressed. So that's interesting, and I don't know any other systems that are doing that. So if you lost the documentation and you needed to know the scan code, right, you could learn it, right? I'm going to hit all the keys and reverse engineer it manually. On the 5110, it's a little different. It shows this 3 and FF. On the 5100, this is the 5110. It's saying key and shows the little symbol associated with that. That's what the DCP looks like. It's got a display command and A for alter and just type in your machine code. All right, some other highlights about the 5100. So last December, there was this Christmas Star Contest hosted by Logiker. Contest, I mean, it was Christmas time, it was just for fun. And his challenge was, however you do it, draw a 17 by 17 symmetric star as and few bytes as possible. So simple little Christmassy theme. The 5100 is handicapped because it only has a 16-row screen, so I can't do 17. You could scroll it, so that was allowed also. So I was put in the wild category for that reason. There's one row missing to make it 17 by 17. It's 17 across, but only 16. But the other thing that I did is you can press space and you can kind of make it flash and flicker. So that put me in the wild category, third place there. The APL, this guy, Peter DeWatcher, in 30 bytes, he wrote the APL, and that's it. Pretty fascinating. I forget the system, ZX Spectrum maybe, and they did it in 28 bytes on that system. I think he used some undocumented opcodes also. So nitpicking there, but pretty impressive. I've understood kind of the math behind what it's doing, but kind of out of time to really talk more into that. So what next? So the system logic manuals have been, I got a physical copy of them. I didn't see them on BitSaver, so I scanned those in. It's not just a manual, they're huge, large posters for each card on the system, so that took a lot to scan those. I recently got a 5120 that also had an unopened copy of all the system logic manuals. They're largely the same as the 5110, except for the disk drive and the power supply is a little different. So I plan on scanning those and putting them, they're on GitHub right now. I don't think they're on BitSavers yet. Yeah, on GitHub. As I mentioned, I have this new front end. It's the same Christian Cordy derived P.A.L.M emulator. I run it on the PC, Windows x86. Remember IBM, a lot of their systems were big Indian, right? So you have to swap the bytes if you're running it on an Intel system. It handles all that for you, runs under DOS, obviously console based. And so that's been fun to work with. You can step, instead of just one instruction at a time, 100 at a time. And that's given a lot of insights about the system. And this display helps me visualize the registers a little more easily as it's going. The 5110 just works a little bit differently. The DCP, all that works in the emulation. I can emulate the P.A.L.M just fine. But in the transition, when it goes from P.A.L.M to kind of starting up the basic, I haven't quite figured that out. So I'm working on a full emulator of the 5100. And also I want to write some code, kind of that core technology. I want to be able to get the 5100 on the internet is kind of one of my goals. Using a Wii modem interface. How is kind of proven it can be done using P.A.L.M. We just have to figure out the right instructions to interface with the external pins. Alfred Arnold wrote the the assembler, so you can write in P.A.L.M. using IBM nobody really likes their mnemonics, right? Christian Cordy came up with a more appropriate style, but it supports both of them. And that's available at this website. Okay, back to this. What's up with this kind of weird symbols in the 5110? I started staring at it a little bit more, and I realized what it is. It's the binary sequence in order. If you start, it's basically null at the top. There's 0 at the top, but then it's 1, shifts over 1, then it's filled in again. It's the binary pattern, and you have an option of kind of what symbol do you want at the top and what symbols do you want at the bottom. You can either have no symbols, and so that's interesting. It just walks through it. So when you're doing kind of decimal to hex conversions, you can do it very quickly. You just have to do it in these funny symbols. That, to me, kind of goes back to the industrial system debugging kind of capability. I don't know if it's unique to the 5110. I haven't seen another system, at least using this symbology specifically. Usually when you're doing hexadecimal, you go through the alphabet A through F, but then you have to search somewhere else to get a 0 through 9. This you can just do it in one shot, just offset, and then you get a choice of how you want those symbols to look at. There's a funny little video on YouTube on what that looks like. Confirm that so everyone complained about the 5100, the screen was so darn small. And I never really understood that. I mean, even back in the day, one of Dr. Wang of Wang, he was interviewed and he says, oh, it's got a small screen. Nobody's going to like the 5100. He also complained no one's going to use A.P.L. and had some other comments about IBM's competition. But even back on the 5100, it has that BNC connector on the back, and you can plug in. I plugged in 14-inch, 9-inch. You daisy chain them together, and they all are responsive, right? There's no lag or latency involved. In the manual of the 5100, I think it sets a limit of like 6 or 7. I haven't quite verified that limit. I found 3, and that all worked fine. As far as I know, these JVC monitors, I think they were harder. It's not like you could just go to Best Buy back in the 70s and get these monitors. I think they were a little harder to get. They were maybe $1,000. So at least for the price, they were hard to get. But they were definitely available even back then. So news and reminders. Typing a lot of machine code gets tedious, right? Every time you power on the system, if you don't have a working tape, that's going to be a bummer on these systems. So I said, all right, how about just a serial interface? So I reversed engineered that. I mean, it's all in the manuals. You can plug right into the A1 board, or I did them both at the same time, or plug in straight to the keyboard. You can use the keyboard, the physical keyboard at the same time. There's no really constraint on that, and so that's been fun to work with, just using an Arduino. I used a fancier ESP32, no particular reason other than I think it has Wi-Fi capability, and I did do that. I did have it where it can work over Bluetooth also, so you don't have to have the wire, but you can tuck this into the system. But it's a serial, so all it's doing is just you type serial into the device, and then it translates it into the scan codes. And so then now I can stream in my basic programs or my DCP, and I have videos about that online. The code's there on GitHub also. Don't just hook up these wires. You do have to have the 330 ohm resistors in line. They're tucked over here, and they're right here on this diagram, these little resistors right here. That's the pull down as the signal comes up that lets it manipulate those bits. When I got a second 5110, but it was lacking a keyboard, so that motivated me to figure this out, the keyboard, and its power supply was broken. I'm not a hardware guy, I'm more of a software person, so I don't do well in soldering. I am trying to get better on that, so don't hate me for that. But so I don't know what's wrong. I think it can be covered. I still have it. So if anyone wants to try it, a hardware person that wants to recover this power supply. But I realize it's all it does is convert AC to these voltages: 5 volts, positive and negative, 5 volts, 8.5 volts, and 5 volts. And there's Meanwell PSU that does all of that. Okay, and it's just 2 components: the Meanswell and this. I think this one's doing the 8.5 volt also, where it's pulling up one of the 5 volt lines to the 8.5. And all that, and I've been using it for the year, a little more than a year. Haven't had any issues with that power supply. I have the dimensions of this board, and it all fits right into the back of the slot. So if you have one that has a busted power supply, there's notes on GitHub on the wiring arrangements. It takes some time. It takes a couple hours to kind of wire these up. Yeah, the notes there. And that's big thanks to BitSavers, like I said, for archiving. Yes, that's kind of my grand vision of understanding P.A.L.M. I think we can do it. I think we can put an ASCII version all in memory. So when you run Bad Apple, it's reading from the hard drive and buffering some stuff. When you transfer it to your IBM PC, it's a number of megabytes. I don't think we'll be doing that on the 5100, reading from the tape. You know, it'll be too laggy. So if you can fit it all in memory, I think we could get a few frames or a few seconds of it going. So that's maybe in a couple years we'll have that available. If you need audio, so the demo scene people, they're kind of partial to having you know, the weird audio in all their demos. You won't be able to do that on the 5100. It doesn't have the built-in speaker. So the speaker capability is limited. One of the demos I have on YouTube, I kind of show you can change really the duration. It kind of gives you a couple little tones, but you can't do you know, even Apple quality music. So it'll be limited, what kind of demo that we put together. So that's all I have. I'll put these online. There's actually a lot more material that, well, yeah, I may have messed up your recording here. I have lots of other charts kind of on my 5110. I have the original invoice of where it came from in Chicago. I have the 5100 I got from a gentleman in Canada that it was used in a hospital, so that's verified. So people did use these systems. That's been fun. What were else? Just kind of more details are in the backup slides that I had. So, all right. Sorry, you had a question?
Yes. I wanted to thank you for a wonderful, very in-depth and very technically accurate presentation. And you were very comprehensive with the entire IBM 5100 and its family. I learned a ton of things I didn't know. The only thing I would comment is no presentation on the IBM 5100 really could be complete without at least a mention of the urban lore and legend of John Titor, the time traveler.
Yeah, I stuck to the technicals. I am fascinated about that story too. I wasn't aware of it until my daughter pointed it out to me. Actually, I brought it home, and she kind of. It's funny because she saw it and knew that lore just by looking at the system. She says that's from that anime. Also, dressing like this, I don't know if that counts as cosplay. I don't know.
It does, and you did that very well.
All right. I'm not normally into that kind of thing, but all right, so I've done that in my life. All right. So what he's talking about, yes, the IBM 5100 is famous for a couple of reasons. One, the online, it was around 2000, 2001, the forum, John Titor mentioning that he traveled back in time. He was looking for an IBM 5100 to solve some problems that are coming up in 2033, 35 in that storyline. He had some pretty convincing evidence, actually. At the time in 2000, nobody knew the relationship of these systems with the IBM mainframe, and he knew all about that it was emulated. I don't know if he ever used the word P.A.L.M, so I'll call him out on that, maybe. Then 10 years later, Japanese crew, they made an anime out of that same story. It's actually a pretty decent anime. It's not as silly as I thought. I mean, I watched through it, and it's, you know, it has some silly moments, but it's actually a pretty good storyline on how they say it. And there were moments that, you know, I got tears in my eyes also, so some sad stories. But my take on it is a story. I view it more as the Back to the Future kind of story. Somebody had some good insights, put a couple things together, came up with this clever story. So that's as much more, you know, I haven't really researched more in that. There is an extensive documentary, I guess, about that on YouTube as recent, I think in 2022, fairly recently, that was put online, and I think that tells that story pretty well. That's more, that's specific, I'll get into it.
Thank you.
All right. So we have mentioned it, we have covered it. All right.
We have covered it, very good.
All right. Any other questions or comments? Encourage everyone to learn about this P.A.L.M machine code. To me, it's, you know, what do we use these old vintage computers for, and just kind of understanding it's just a clean system. There's no pop-up ads. There's no, you know, disruptions. I can get right on the hardware. I can do my P.A.L.M assembly. I can talk directly to the screen. I can build an interactive program. It's helped a lot now that I have that serial interface, so I don't have to retype. A lot of people, they haven't gotten the disk drive systems to work on their system, so those are starting to fail. The tapes themselves are starting to fail, so those are getting limited, that people can enjoy the systems more by being able to save files to tape. So we're helping to preserve some of that. I will point out one, just if you know nothing else about the 5100, know that the 5100 has a white face, the 5110 has a black face. So do be aware of that if you're looking for one. Don't let anyone claim it's a 5100 if it's got a black face. Just a reminder on that. So, all right, that's it. All right. Thanks. All right.